Recording. All right. All right. A few things. Okay, so I'm gonna go through the announcement first because that's how I keep track of what I need to talk about in the class. Because if I don't do this, I will forget. All right. So the agenda starts with what I observed in the previous homework. I mean, not homework, the lab. So with the 3 by 3 adder lab, some people did not turn in a file, and so those people did not get points. Those 4 points for the adder circuit file. Um, this part is mine. Okay, I'm owning this part because quite a few people did not name the main circuit main, but I did not put main in double quotes in the instruction. So I guess people do not know that. Oh, okay, I'm supposed to name the circuit main. So that part is on me, and I'm not taking points off of anyone. A few people put the pin locations at the wrong places, so they were not reading the instructions in the lab, and they were just copying what I did in class, according to those pin locations. So those people lose 1 point because of the incorrect pin locations. Um, a few people also did not test the circuit before submitting. Um, that's the whole idea of giving you guys the test circuit to begin with, is you can test it before you turn in the file. So some people, I think at least one person was using the wrong type of pin, like an input pin instead of an output pin, and that would have been easily tested out using the test circuit that I provided, and you know so the bottom line is, if I give you a test circuit, a way to test your circuit before you turn it in, use it. It's me trying to help you to get all the points possible. All right, so having said that, we are moving on to a new topic today, which is about floating point numbers. So now, I mean, normally, okay, I would say before 2023 or so, floating point number as a topic is like, why do we care about floating point numbers? But these days, we do care about floating point numbers. Why do we care more about floating point numbers now than, say, 3 years ago? What happened in 2022? The rounding. That happened, I think, before 22. But you're correct. Floating point numbers definitely have rounding issues, even on values that we do not think that should be a problem. That's because floating point numbers are in base 2, and we do base 10 numbers. So what seemed to be easy for us, like, point 1, okay? Point 1, in decimal is like super easy for us. But in binary, it would take an infinite number of digits. It's a recurring pattern in binary. Kind of like, how you would represent 1 divided by 3. How do you represent 1 divided by 3 as a base 10 decimal number? It's 0.33333, and it keeps going, right? And it's the same thing with point 1 in base 10. If you want to represent it in binary, it would actually be a recurring pattern of the digits. Okay, so you're correct. But that's not why it is important now. It has to do with LLMs and GPTs and stuff like that. So why do you think that is important? Okay, so you look at all the models, all the GPT and the LLM models, and they all specify, or one of the parameters or one of the characteristics of an LLM is the number of parameters. What is a parameter when you look at a GPT or an LLM specification? Nobody knows. Okay. And you're in computer science or you're on your way to computer science, this is important stuff, okay? So if you don't know what the answer is, I would suggest you to take a quick search because it is relevant to what we are studying, okay? So you can ask, what is a parameter in the specification of an LLM, okay, either LLM or GPT? Okay, so I'm just going to ask this question to Google. And the parameter refers to two different things. One is the internal parameter and the external API parameter. And I'm referring to the internal parameter. So the internal parameter means it is basically a number. Okay, a parameter is a number. It is a quote unquote real number. But in a computer, you never really have real numbers. You only get floating point numbers. And that's basically what it is. Okay. So that means if you can do calculations really, really fast with floating point numbers, then you have just sped up, all the AI or the LLM, GPT, any type of neural net based, technology can be accelerated if you figure out how to do addition and multiplication really fast with floating point numbers. Are we doing okay so far? Kind of giving you a context, a modern context of why floating point numbers are important. Are we doing okay? All right. So, what exactly is a floating point number? Well, in the very typical way that I teach classes, we'll start with something that you already know, okay, or supposedly know. So we're gonna start with. I'm looking for my little text editor here. I'll bring it to your view. And I think at some point I'm going to transition to use the tablet, but right now I don't need that. So let me ask you what exactly is 1.67 e minus 3. Okay, so have your CISP 360 professor talked about the floating point notation. This is not a floating point notation. This is what we call a base 10 scientific notation. So have you been taught, okay, the scientific notation in your C++ class, CISP 360? Okay, I see a whole bunch of nods. So can I assume that you know this topic already, or do you guys need me to talk about it? All right, I'm not, okay. Okay, we'll talk about it a little bit. Okay, so we can talk about this. So this is essentially 1.67, which is in base 10, times, okay, times, okay, 10 to the power of negative 3. That's the notation. In other words, this part here is known as a coefficient. Whatever that is just copied here. And then the little case e or the lowercase e is essentially a separator. It separates what we call the coefficient from the exponent of 10. So negative 3 in this case specifies the exponent of 10, which specifies the unit that is associated with the coefficient. All right. So together, this is called the base 10 scientific notation. You have a certain coefficient, you specify the exponent of 10, and this is how you combine those two to specify a particular value. Okay, are we okay with this? Are we all good with the concept of exponent? Okay, excellent. So now the big question is, why do we have to deal with stuff like this? Well, because in astronomy and also in engineering, a lot of times we have to deal with huge numbers and tiny little numbers, right? What is the size of a transistor on a inside the IC right now, like a production one? Okay, if you look at the Apple M4 chip, what is the size of a transistor? It is 2-ish, 3 nanometers, right? So what exactly is a nanometer? It's a little smaller than that, okay? So if you don't know the answer, it's okay. Sometimes I cannot remember those terminology either. So you look for it, right? So instead of waiting for me to give you the answer, you have your phone, you have your computer, you can just look for what exactly is a nanometer. 10 to the negative 9. Okay, so if a transistor is 2 nanometer and I want to express everything in meters because that's the SI unit, how do I write it? It'll be point 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be the number. So basically, 2 nanometer is this many meters. Okay, So do you want to write all those zeros after the decimal point every single time that you refer to a nanometer? Probably not, right? So this is why we also can say, oh, okay, in terms of scientific notation, we can now say it is just 2 times 10 to the power of -9. Done. Super easy. Is that okay? So this notation is in C and C++, and this is why CISP 360 is such an important prerequisite of this class. Okay, because if your professor taught this concept in CISP 360, which they're supposed to, then you go to this class and go like, oh, okay, I get it, because it has been talked about already. Question? Yep. Yep. So let's talk about the speed of light in meters. Okay. So what exactly is the speed of light in meters per second? Okay. So don't look at me. Okay. Go to your phone and just ask it, right? Hey Google. Okay. I guess I have to. Yep. Hey Google, what is the speed of light in meters per second? And it is 2,299,792,458 meters per second. I think it's okay to call it like approximately 300 million. Okay, so you go like, okay, what exactly is 300 million? 300 million. 1, 2, 3, 4, 5, 6 meters per second. Okay, well, do I want to really write that many zeros every single time? No, we just say 3e8 because it is the same as 3 times 10 to the power of 8. So in scientific notation, well, it's easy to write. So is that okay? Does everybody understand why the scientific notation is handy? Do we actually need it? No. You can put all the zeros in if you want to, okay? But is it handy to have it? Absolutely, okay? Now, on your calculator, okay, depending on which calculator you have, how you use the scientific notation on a calculator can also be a little tricky because on your calculator, there are two buttons, okay, that can be extremely confusing. One is the actual E or Euler's constant, or Euler's constant to the power of something. That button is labeled E and then with an exponent of x or something. And there will be a different button that is responsible for you to enter, that's responsible to kind of take the role of the little e here that specifies, oh, okay, this part here specifies the exponent of 10, not the coefficient. Okay, so what if you are to kind of put this into a online calculator? So is it going to look at the E as a part of the scientific notation, or is it going to look at the E as Euler's constant? I don't know. I cannot tell you. It depends on which calculator you're using. So that means any type of math related to the scientific notation, you have to be careful which calculator you're using and whether the E is referring to Euler's constant or it is referring to the scientific notation, the separator between the coefficient and the exponent of 10. Is it? Yep, go ahead. You will not have a decimal value. So after the e, it is only going to be an integer. It can be zero, but it can be zero. It's not about why. It is about so e 3e0 is just 3 because it is 3 times 10 to the power of 0. Yep. All right. So this is scientific notation. So now we're going to move on from base 10 scientific notation to something like this, but in binary. Okay, so we are going back to base conversion for a little bit of time. So let's say I have a quantity in base 10 that I see as 26.625. Let me double check. Yep, 625. This is in base 10. And I want to convert this to a binary number. How would I do that? Now, this is something that we have talked about already, so you should be able to do it on your own. Okay, now how quickly you can do it is another question. I don't expect people to be able to do this like super fast, but you should know how to do it. Okay, so on a piece of paper or on your own computer, you can kind of go through the process and see if you remember how to do this. One really good starting point is by listing all the powers of two that you think would be relevant in this case. Okay, so let's go ahead and do that. Okay, I think 32 is kind of like too much, but it's okay to start with 32. Then we have 16, then we have 8, then we have 4, 2, 1, and then we have a half, a quarter, and I think eighth is all we need because in this case, because 625 is or 0.625 can be seen as a multiplier times 1/8. Okay, so now we just have to say how many of each power of 2 do we need in order to make up 26.625. I hope you guys still remember that process. When we talked about base conversion, we kind of went through this process a few times. And I can guarantee you that exam 1 will have questions regarding base conversion. So, knowing how to do this and at least knowing, okay, I know the process, okay? And I think some of you are already done on the piece of paper. It's like, Tech, I got it already. Great. Okay. So in this case, we have none of 32. So I'm just going to write the number here. None of 32, one of 16, and then after that, we have one of 8, none of 4, one of 2, none of 1. And because that's our 2 to the power of 0, so we put a point to separate the digit corresponding to 2 to the power of 0 and 2 to the power of -1. So we have 1 of half, none of quarter, and 1 of eighth. So this is the base 2 representation of 26.625. Are we doing okay so far with that conversion process? We're good? All right. Cool. All right. So now we look at this and go like, what if I were to multiply this or divide it by 2? Okay. In other words, I'm asking you what happens when I take this number in base 2 and I divide it by 2. So what is the binary representation of this thing after the division by 2? Yep. But to which side? To the left. That is correct. Okay. So that means after this division, okay, we just take this number here in base 2, paste it, and then we just go like, done. Okay. Why does that work? Because the number is in base 2 and I'm dividing it by 2. So what used to specify um, a half is now specifying, the quarter, and what used to be specifying, the ones is now specifying the half because everything is divided by 2. Okay, so in your mind, are you kind of understanding how the math works out? You good? All right. So what if I were to kind of do something really stupid and multiply the whole thing by 2 again? Then you go like, okay, cool, that's that, right? So the reason why I'm dividing by 2 and then multiplying the whole thing by 2 is because I want to change the representation of the value, not the value itself. I want to preserve what I'm representing, just what it looks like. Is that okay? So that means if I call this value x, okay, this x has nothing to do with subtraction or addition. I just kind of use the variable net x here. I can still maintain and say that, well, these are all representing the value of x. They just look a little bit different. Are we good so far? Yes. Yep. Okay. So X is representing the actual value that we want to represent, which is what we see as 26.625 in base 10, which is also known as 0.11010.101 in base 2. Okay, but I want to re-express it in this case as, oh, I just changed the coefficient and then times 2 to the power of 1 in this case. Okay, in other words, I'm adding one more thing which looks really absolutely stupid because it is not necessary. Okay, um, can I move that decimal point one more place? Like it becomes 10110.10101 in base 2, and can I make an adjustment over here so that it is still maintaining the same value that is being represented, but the format is a little bit different. What should I put here if I want to change the coefficient to have the decimal point to move to the left hand side by one more digit? Can I make it up by changing the exponent of 2? Okay, so what should be the new exponent of 2? 2, very good. Okay, so we are observing a pattern here because even in the original number, I can already say, oh, yeah, we are multiplying by a power of 2, except that is 2 to the power of 0. So are we seeing a pattern here? Okay, so we are starting out with a concrete example, and then we are moving down and trying to see, oh, I think there's a pattern. Okay, so now you guys are probably thinking, I hope you're thinking, so when are we going to stop, right? We can keep moving that decimal point to the left-hand side. At some point, we're going to stop. At some point, tech is going like, okay, this is where we're going to stop. So we'll go like, okay, we keep going until we get to this point here, until we have 1.101. Ooh, it just turns out that way. Okay, nope, there we go. All right, so tell me what is the exponent of 2 in this case? How many times have I shifted the decimal point? 4, that is correct, okay? You go like, okay, cool. Does that remind you of the base 10 scientific notation? Do you see the pattern? Okay, if you see the pattern, if you're nodding, great, okay? Because this is exactly what I want you to see is, oh, I know base 10 scientific notation, okay? Because even though I may not have learned it in CISP 360, all it really is about is there's a coefficient, and then we multiply the coefficient with a power of 10. That product is the quantity that I want to represent. And we are now doing exactly the same thing. What is that? Oh, I think it's just the air. Yeah, it's the air conditioning, you know, pushing the air through the gap of the door. It has a little reed effect. So the door becomes a woodwind musical instrument. Pretty sure that's the starting point of a lot of ghost stories. Yep. It's like it's just a door. Okay. All right. Getting back to this. So now we have a coefficient, except it's expressed in base 2, multiplied by a exponent or a power of 2. So it is the same thing as a base 10 scientific notation, except everything is in base 2. Are we good so far? So in essence, this is a floating point number representation. It is broke, so a value is represented by two parts. The first part is the coefficient. The second part is a power of 2. And by maintaining the product of those two, now we can specify the value that is being represented. Are we good so far? Yep, go ahead. Not exactly. Not exactly. So the reason why we call it floating point is because it's actually a misnomer. We want the point to be exactly at the same place for every single number. and we adjust the exponent of 2 so that we always have 1 point blah 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 times 2 to the power of something. Okay, all right. So now we introduce a new concept. Okay, so instead of calling something a coefficient, now we have the concept of a mantissa. So the concept of mantissa is a mantissa, okay, a mantissa is a coefficient. Okay, so we'll call the mantissa m, okay, in base b is a coefficient where the mantissa is, let me see, I have to remember, is less than, so m has to be less than b, but it has to be, I'm trying to think, remember, it is at least 1. Okay, there we go. So it's 1. So this is the constraint of m. It has to be at least 1, but it has to be less than whatever base we are starting with. Are we good so far with the constraint? Yes. In a way, you're correct. So in floating point number representation, 0 is a tricky thing. So we'll talk about how 0 is actually represented. But in the case of a mantissa, this is a restriction of a mantissa. It has to be at least 1, but it has to be less than b, which is the base that we're working with. So what that means is if you have a number, okay, so in base 10, okay, so I'm switching back to base 10, in base 10, and if you want to say, oh, 300 E6, which is also the speed of light in meters per second, but this is not what we call a normalized floating point number because 300 is not a mantissa. It is a coefficient, but it is not a mantissa. So if you want to convert this to what we call a normalized floating point number or a normalized base 10 scientific notation, then we have to go like, oh, okay, this is okay. Because this 3 here is in fact greater than or equal to 1, and it is less than 10. Is that okay? So mantissa is really just a special term that we call a coefficient when it meets this particular special requirement. Are we good so far? Cut it into pieces. What cut what into pieces? So when you want to fully represent a number in scientific notation, then you have to figure out, what should be the mantissa and what should be the power of 10 when you're dealing with base 10. But it's the same approach when you're dealing with base 2 scientific notation, which we just did. Okay, so when we looked at the previous example in base 2, we started off with a particular value that we want to represent in base 10, and then we convert that straight into a binary number that is not using the floating point notation. So this part here is not using the floating point notation at all. Okay, it is just a base 2 number with decimal values, right? So, but when we did all this stuff here, okay, then we are starting to move the decimal point closer and closer to the left-hand side until we have a mantissa. This is the mantissa in base 2 because you asked those two questions. Is the value represented by the highlighted portion? Is it greater than or equal to 1? Pretty sure it is. Is it less than 2? Yes, it is, because in base 2, how is the quantity 2 represented? It is 1, 0. So I think we can all at least understand that, oh, okay, this value, whatever that is in base 2, has to be less than 2, has to be less than 1, 0 in base 2. So now we have established that the highlighted portion here can in fact serve as a mantissa because it is greater than or equal to 1, but it is also less than 2. Is that okay? And what about the quantity that we actually want to represent? Well, we just have to specify a power of 2 to multiply the mantissa with so that the product between those two becomes the value that we actually want to represent, which in this case is what we know as 26.625 in base 10. So are we doing okay so far in terms of the notation, in terms of, oh, okay, so we want to represent values that can be huge, that can be tiny, but we want to represent it using two parts. The first part is called the mantissa, and then the second part is the power of whatever base you're working with, in this case, base 2. We good so far? All right. So now we can get back into the notes, okay, using my notes here. Nope, that's from the previous class. So let's go to the floating point number module, which has a lot of math in it, but it's not really the kind of math that you learn in calculus or linear algebra. It is in a way easier and in a way harder, depending on how you look at it. So we'll go take a look at floating point number representation. So what we see as a double, okay, okay, how many people know about double, double, spelled exactly that way as a type in C++? I think all of you should raise your hand, okay, because I think that was introduced in CISP 360. So double is really just a abbreviation of its true name. The full name is an IEEE double precision floating point number. Okay, but do you really want to spell this out entirely every time you want to refer to the type that we know as double? Probably not. Okay, if we don't even want to spell out integer as integer and instead we use int, we probably don't want to spell out IEEE double precision floating point number. Okay, so that's why we just call it double. Interesting. What is it about? All right, I'll pay later. Which I do actually every time they have a fundraising event. I do pay for that. All right. So the best part of the Wikipedia representation is it gives you a picture and it gives you some math equation to basically say how do we interpret the value represented by a double. All right. So now we take a look at this, go like, it's color coded, right? So the first part here, which is bit 63, it is called the sign bit. It controls the sign of the entire quantity. Okay. And then we have these 11 digits that is called the exponent, but it's not really the exponent. It is called what we call a biased exponent. And then the pink portion is not the mantissa. It is the fraction of the mantissa. Okay, so all of those words that I used, like what is a biased exponent and what is the fractional part of the mantissa, they are they sound really confusing. Okay, so the best way to look at the actual value represented by a double is to look at the formula. And I believe that I also have my own representation of the formula in my own notes. So let's go check out how I represented the whole thing. Okay. There we go. This is the way I like to do it. It's about the same thing. So I use the very typical format, okay? VDF. This is the double it is the value based on the double interpretation of a bit pattern F. In other words, F is an array of individual bits, okay? F underscore 0 is bit 0 of F. F underscore 63 or F subscript 63 is the most significant bit of F. So F is basically an array or vector of 64 bits. Is that okay? And I'm using the subscript notation to designate which bit are we referring to. Okay, so that's the subscript notation, which we have been using for how long? I think since we talk about number representation, we have been using the subscript thing to refer to a particular digit of a sequence of numbers, okay, or digits. All right. So we look at this, okay, and I say, oh, the entire thing is, this particular, this is the value. This is how we interpret what value is being represented by f, which is really just a vector of zeros and ones. So what do you do when you see something horrendous like this? Yes, I did use the word here, horrendous, because from the first time you look at this, it is supposed to be horrendous. But is it really horrendous, or is it really just, yeah, kind of tedious? What do you think? Well, we work on this one step at a time. Okay. Whenever you see something that seems to be really difficult to understand or it is really complicated, what do you do? I'm posing that question not as a question for CISP 310, but as a general question. When you see something that seems to be very difficult and complicated, what do you do? Yep, break it into smaller parts. Exactly. Okay, you break it into smaller parts and then you look at each smaller part and you ask, do I understand that? Okay. And if you do, you might need to jot down some notes and go like, okay, this portion means this. Okay, I can interpret this portion. Then you move on to the next portion and go like, okay, do I understand that part? Right? In other words, the worst approach of looking at this thing here is to throw your hands out and go like, I'm not sure what it is. I don't want to know, because that will get you nowhere after you graduate and you want to get a job. This also would be a good time to tell you something about this weekend. So, over this weekend, I had an opportunity to talk to the project lead of a, I would say, medium-sized company in Sacramento. Okay, so they're going through a lot of growing pain. Okay, because the company is growing really rapidly, but it's still a relatively small company. I think they have somewhere around, right now they have around 50, no, about 5,000 employees. It's not a whole lot, okay? It's not a gigantic company. And for each software engineering opening, they get about 50,000 job applications. The company is called VSP. Okay, some of you might have heard about it, especially if you have parents who work for the state. But most people do not know what VSP is. Okay, it is an insurance company for vision stuff. Okay, for optometry, eyeglasses, that sort of thing. So it's a fairly specialized, kind of niche kind of company, and they get 50,000 applications for a single software engineer position. That's the kind of market that you'll be entering in about 2 years. Okay. So I do want to kind of share that with you, kind of in the context of this thing here, because, you need to figure out a way to learn without a professor. So my job here is to work myself out of a job. If I do my job properly, I won't be needed anymore. Okay? Because that is what you need. It is not about what I need. I want my income, I want my job, okay? But from your perspective, you need to learn how to learn to the point where you don't need a professor or a mentor or tutor anymore, okay? So that's the long-term objective. I'm not saying that, okay, from today on, I'm not going to be in the class anymore, and I'll just give you one really, really difficult final exam, and we are done for the semester. No, that is not going to happen. Okay. But I do want to show you, what you need to do in the next 2 years. Okay. In the next 2 years, you need to learn how to learn. Okay. So we'll start with this. We'll separate it into smaller portions, and we're going to look at just this portion here. -1 to the power of f63. What does that mean? F63 is referring to the most significant bit. Just like any other bit, which is a binary digit, it can be a 0 or a 1. So if the sign bit is a 0, then we are looking at -1 to the power of 0. What is negative 1 to the power of 0? What value is that? Hmm? It's just 1. Okay. And what if f63 is a 1? Then you have negative 1 to the power of 1, which is just 1. In other words, oh, Tack, you're just using some really tricky stuff to say that if f63 is a 1, we are specifying a negative quantity. If not, we're specifying a non-negative quantity. Yep, that's exactly what it is. F63, or the most significant bit of a double, its only job is to say, is this value overall speaking, is it negative or is it non-negative? That's the job of F63. So now we look at this portion here, which also looks horrendously complicated. Well, it is long, but it's not really complicated. 1 plus, I think we all get that part, right? So now we look at the other part, and you go like, wow, this is really kind of complicated. I goes from negative 52 to negative 1, and then we pick out the digit called f of 52 plus I, and then we multiply that bit by 2 to the power of I. What exactly is going on here? So when you see anything like this, what you can do is to say, I'm just going to take a look when I is the minimum. Okay, when I is the smallest number, which is negative 52, what is going to happen? So when I equals to negative 52, which is the low range of the range in the sigma notation, then you have 52 plus negative 52. So we're looking at bit 0 in that case. Are we good? So what are we multiplying bit 0 to? It would be 2 to the power of actually negative 52. So that means bit 0 is specifying whether we have or not 2 to the power of negative 52. Tiny little number, right? But it's really just indicating, do we have it or do we not have it? What happens when I equals to negative 51? Then we're looking at the bit 1, and then it will tell us whether we have 2 to the power of negative 51 or not. Oh, that is kind of like base conversion, except we are shifting just the numbers a whole bunch of times in order to figure out what value we're adding. And that's exactly what it is. So now you go all the way to what happens when I equals to negative 1. Then we are looking at f of 51. It specifies whether we have a half or not. Oh, okay. So if I were you, and this is new to me, then I would go to the picture where the floating point representation is. Okay, so I'm going to go back to the Wikipedia page, and then we go straight to here. And if I were you, I would just go like, okay, I would kind of make a little pointer here to that least significant digit, and I will say, okay, this is just telling me whether the mantissa has a 2 to the power of negative 52 or not. And then I go all the way to the other one, to the other extreme end of the pink portion, and I'll say, oh, so this is telling me whether the mantissa has a half or not, because it's 2 to the power of negative 1. So that's what I would do, okay, if I were you. And Batak, you did tell us that the mantissa is supposed to be greater than or equal to 1 and less than 2. So if I just add this is 1/2, this is the quarter, this is an eighth, all the way down to this is 2 to the power of negative 52. If I add up all those powers of 2, it will still be not 1. Okay, it will be very close to 1, but it won't be 1. So why is this the mantissa? I never said this is the mantissa. This is the fractional part of the mantissa, which means there's another part of the mantissa, the non-fractional part. Where is that part? That other part is here. That's why we have a 1 plus. The 1 plus is what makes this entire thing in the parentheses to be greater than or equal to 1. Because even if you have all these bits here, all the F digits, even if they're all zeros, guess what? You still have the 1 plus on the outside. You cannot get rid of the 1 plus. Are we good so far? This is also why F0 all the way up to F51, those bits are called the fractional part of the mantissa because they are excluding the 1 point of the mantissa. Because in base 10, okay, you cannot just exclude something because in base 10, what can be the digit that is to the left hand side of the decimal point? It can be a 1, can be a 2, can be a 3, and all the way up to 9. Cannot be 0 because the mantissa has to be at least 1. Cannot be 0, but you do have 9 choices other than 0. But in base 2, you don't have a choice because in base 2, you have 2 digits to choose from, and 0 is not a possible choice. So you only got one choice left, which is the constant of 1. Is that okay? That is why the pink portion is called the fractional part of the mantissa. Okay. Okay, cool. So now we get the sign, we get the mantissa. Okay, so everything in the parentheses specify the mantissa, but the sigma notation only handles the fractional part of the mantissa. What about this portion here? That also looks horrendously difficult to understand. Well, once again, we do it one step at a time. We are raising 2 to the power of this expression. That expression looks pretty complicated, but it's not. Because once again, we're getting back to base conversion. And you plug in, what if I equal to 0? When I equals to 0, then we're looking at f underscore 52, which is bit 52 of the entire bit pattern. What are we going to do with that bit? We multiply that bit by 2 to the power of 0. In other words, bit 52 specifies whether we have a 1 or not. What about when I equals to 1? F of 53 tells us how many 2's do we have, and so on. So when I equals to 10, then we are looking at bit 62, and that will tell us how many 2 to the power of 10s or 1024 do we have. So we now have 11 bits specifying 1, 2, 4, 8, all the way up to 1024, the presence or the absence of those powers of 2. Add them all up, and then you have the quantity specified in the parentheses. Now, that number has to be at least 0, and it can be at the most 2047, because 2047 is 2 to the power of 11 minus 1. Okay, so that's why I know the range. Then you go like, so without the minus 1023, that means we can only have a non-negative power of 2, which doesn't seem reasonable because how do we represent the charge of a single electron? You can't because that's a really tiny amount, so you have to specify 2 to the power of negative something. So how do we handle the negative? This is the IEEE method to do it. They subtract what we call a bias. So 1023 is known as the bias for the biased exponent. So are we doing okay so far with all this explanation? Yes. Ah, okay. Does this answer the question? Go ahead. There are, so double is not the biggest, there's a quad. Okay, so what is float? Okay, if you in CISP 360, float is a type. Okay, so float as a type is what we know as a single precision floating point number. A double is a double precision floating point number, and you go like, so the next one is triple. No, we go by powers of 2. So the next one is a quad. So there is a quad precision floating point number that takes 128 bits. So it has a much larger range and also precision compared to a double. So does that answer your question? Okay. I only choose to use double because that's the most common type that we use to represent quote unquote real numbers. Are we doing okay so far? All right. All right. So once again, okay, when you see something that seems to be horrendously complicated to begin with, just break it into smaller parts, and as you figure out each one of the smaller part, take notes, because if you do not take notes, by the time you figure out the last one, you would have forgotten about the first few parts. So I would take notes. Now you go like, but Tech, you seem to remember everything about the floating point number. Well, that's because I've been teaching this class for at least 15 years, and you are not in the same boat. And I'm also not moving forward to try to get into the private sector and become a software engineer and have to compete with the other 49,999 applicants for that one job as a software engineer job. I don't have to deal with that. In 6 years, I'm retiring. So I'm in an entirely different boat compared to you guys. Is that okay? I just want to make that very clear. You guys have a, I'll just say, interesting journey ahead of you, because I really cannot tell what's going to happen in the next 2 years when it comes to employment. This is also something that I got out of the conversation over the weekend. Do you guys know what is 996 as a work schedule? It's being used by most of the Bay Area companies, big companies and startups. What is 996 referring to? Yep. So you work 6 days a week from 9 a.m. to 9 p.m. And I would probably add at least. That's the work culture currently. That's the work culture in the Bay Area, and it's creeping into the Sacramento area now. Okay, in the Bay Area, there are a lot of employers who advertise as like, oh look, we treat our employees really great. Every person gets these 2 weeks of vacation days and whatnot for every year, but no one dares to take vacation days. So they all accrue the vacation days, but nobody takes vacations. Why? So you have to look at it from the perspective of the employer. Okay? So from the perspective of the employer, what happens when TAC decides I'm going to take the next 2 weeks off because I want to go on a cruise? So what happens to the project that I'm working on? It's going to be stalled for about 2 weeks, right? And the employer goes like, maybe I should call up those 49,999 candidates and see who's the next one in line, because I cannot afford to have this project held up by tax vacation for 2 weeks. Okay? So the company call up the next most suitable candidate, and that person turns out to be available. So that person comes in and go like, yeah, I can take on the tax job, and I will finish it before he returns from his vacation. So in 2 weeks, I come back from my vacation, and what do I find? I find out that my key card cannot open the door anymore. Yes, that won't work anymore because AI can actually read your code and document it for you. Give it a try, okay? I challenge you guys to give that a try, okay? Write the most obscure code for no particular reason, okay? And submit it to ChatGPT and say, I want you to document what this code does, and see what happens, okay? At least give it a try, okay? Because until you try it and actually see the result coming back from ChatGPT, you would just go like, "Oh yeah, tech is just hallucinating." No, I am not the one hallucinating. Okay, it is creepy how much AI can do already. Okay, you can even turn in all your CISP 360 homework assignments. Okay, assuming you actually did all the work, and turn that into ChatGPT and ask, how can I improve this code? and see all the feedback coming back from ChatGPT. I was actually surprised. I actually write code because I have to write code to generate the exam questions for you guys. And I turned that code into ChatGPT and asked, okay, are there any ways for me to improve this code? It came back with a whole bunch of stuff. Okay, because I have some dead functions that I don't call anymore, and they don't work. And ChatGPT would go like, hey, this function is not going to work. There's no way this function will work, and would give me suggestions of how to fix it. Yeah. Yep. So that's why people don't take vacations. That is the kind of work environment that many of you are looking into, assuming things do not change in the next 2 years. Am I? I do not mean to scare anyone, okay? But at the same time, I also want to let you guys know what you're stepping into, okay? So that you'll be prepared for those days. All right. So what we're going to do next, we have time, is to take a look at the example that I have given you and go like, okay, let's turn this into a double. What turn what into a double? Our 26.625 will turn it into a double. Okay, so let's make it even more fun. Let's make it a negative number. There we go. So everything is now negative. Okay, so I'm just adding a negative in front of everything. There we go. Okay. So now, how do I turn x into a floating point number? First thing first, f of 63. Okay, so f of 63, oops, I said 63, but I typed 64. That has to be a what? Should it be a 0 or should it be a 1? It should be a 1 because I'm trying to specify a negative quantity. Okay, that's kind of easy. All right, next thing is what happens to f of 62 all the way down to 52? Okay, so just to refresh your memory, actually I can reposition my screen so that you can see both. I can just scroll this one up a little bit like so. You can see the top, and then I can now work on this one here. So in other words, I'm asking you, what should I specify these 11 bits? In other words, what happens to f of 52 to f of 62? Okay, what do you think? What do I want these to represent, in the sigma notation? The actual exponent of 2 is this. But so if we're looking only at the 4, that's pretty easy. But we want this quantity not to specify 4, but what? Because the 4 is after the subtraction of 1023. So before the subtraction of 1023, what is the unsigned value that we need to represent? 1023 plus 4. Okay, so now we are looking at this has to represent 1027 in base 10. You go like, but Jack, we want binary numbers, we want digits, right? So that's actually pretty easy because this is 1024 plus 2 plus 1. 1024 itself is a power of 2. So once I take care of the 1024 out of 1027, I only got 3 left, and 3 is an easy one because it's just 2 plus 1. So now we look at this and go like, oh, okay, so we are looking at 1 followed by 10 zeros because that 1024 is 2 to the power of 10, which means in binary it is 1 followed by 10 zeros. So it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. But then we also have to remember to add the 2, which is a 1 0, and then to add the 1, which is really just 1. So that means when we combine everything, it is 1, and then followed by 8 zeros, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 1 in base 2. So these 11 digits specify what I need from bit 62 down to bit 52. Are we doing okay so far? We good? Okay. All right. So now we go one step further And then we ask, what about the rest of the bits? Okay, what about from 51 all the way down to bit 0? Well, that's specifying the fractional part of the mantissa. I know my mantissa already, okay? This is my entire mantissa. This part is the fractional part of the mantissa. So that means this portion is really just 1010101, and then a whole bunch of zeros in base 2. Are we doing okay so far? The most important point is the 1 point, okay, is not represented anywhere in the bit pattern F. It is only storing the fractional part of the mantissa. Are we good so far? So now we stitch everything together, okay? So we have a 1 followed by 1 followed by 8 zeros, 1, 2, 3, 4, 1, 2, 3, 4, 1, 1. And then we just have 1, 0, 1, 0, 1, 0, 1, and then a whole bunch of zeros after that, okay? So when you look at this and you go like, okay, tag, but we really want to see the entire bit pattern, you probably don't want to hear me count the number of zeros that I need to put here. This is the disadvantage of base 2. You need a lot of digits to represent anything. So what do? We go like, let's not use base 2. We'll use base 16 instead. Have I talked about base 16 in this class? No? Okay, it's easy. So in base 16, you just need a lookup table. Okay? So we have base 2 on one side of the table, base 16 on the other side of the table. 0, 0, 0, 0 in base 2 is 0 in base 16. Does that make sense to you? I hope so. The next one should also make perfect sense. Okay, cool. 0, 0, 1, 0 is 2, 0, 0, 1, 1 is 3, 0, 1, 0, 0 is a 4, 0, 1, 0, 1 is a 5. So far you guys go like, oh, okay, this is just a regular base conversion. We have seen this already in the number wheel, right? Okay, so we'll keep going. Okay, this is a 6, 0, 1, 1, 1 is a 7, 1, 0, 0, 0 is a 8, 1, 0, 0, 1 is a 9, and the 1, 0, 1, 0. Oh, wait, we have a problem here because we don't want to make this a 10 because that's in base 10. So in base 16, we borrow characters from the English alphabet. So we just call this A, 1011 is B, 1100 is a C, 1101 is a D, 1110 is a E, and then finally 1111 is a F. So this is how we have 16 unique digits in base 10, in base 16, sorry, in base 16, which is also known as hexadecimal. Okay, it is not just hex, it is hexadecimal. Hexa is 6, deci is 10, so together it means 16. Okay, so this is base 16. So some of you might have recognized and go like, I have encountered random, seemingly random strings, involving 0 to 9 and A to F in multiple places, especially those of you who have to help your uncles, aunties, grandparents, and whatnot to set up their Wi-Fi routers. hmm Because sometimes you have to look at the MAC address of a router. So I have one that is running right now because otherwise my tablet would not be running. So it has a MAC address of 9483C4 5C8429 because those are hexadecimal digits. IPv6 also makes use of hexadecimal digits when they specify an IP address. So hexadecimal is actually quite useful. Okay, if you work with computers, if you work with networking equipment, you'll be dealing with hexadecimal numbers eventually. Are we good so far? Yep. So we don't use octo as much because these the problem with octo is one octo digit is corresponding only to 3 bits, which is kind of like there are 8 bits in a byte, right? So if an octal is only 3 bits, then you need almost 3 digits. You need almost three octal digits for each byte, and it's not even at an even boundary. So that's why most of the time we don't use octal. In the past we do. Okay, people use octal digits a lot in the past, but these days because we have hexadecimal digits, so we just stick with hexadecimal digits most of the time. But they do exist, and old timers use octal a lot. And this is also why in C++ you use octal to specify non-printable characters. Yep, yep. So what kind of non-printable characters are we talking about? Okay, let me show you something that you probably should have seen, but you may not take note when you saw it, or your professor did not show it to you. All right, so we'll take a look at the ASCII table. Okay, this is why I like Linux, because everything has a man page, has a manual page. This is called the ASCII table. So the ASCII table is, on this side is super easy. It's telling you the character uppercase D has a hexadecimal representation of 44, has a decimal representation of 68, and an octal representation of 104. They all mean the same thing. Because what is 44 in binary? Okay, can someone quickly convert from hexadecimal back to binary for me? What is 4 in binary? If 4 is a single digit in hexadecimal, what is the corresponding bit pattern that you just wrote down, hopefully? I, I'm also testing whether people are actually taking notes or not. 0100. That is correct. 0100. So that means the lowercase, excuse me, uppercase D is the binary bit pattern of 01000100. So when you use 8 bits and specify in that particular order and you send it to a printer, the printer is going to print uppercase D. That's what ASCII is representing. Okay, it's assigning an 8-bit code to each character. Okay, so A to Z punctuations, super easy to understand. What about this crap over here? Mm. So this crap over here is like, what is BS other than bullshit? So BS turns out to be a very important control character. It is backspace. Every time you press backspace on the keyboard, it is sending backspace, which in this case is 08, which means it is literally the bit pattern of 00001000. It's sending that code over from the keyboard to the computer. Now, not quite that because your key code is a whole different thing, but we can kind of imagine in the head that this is the code corresponding to the backspace key. Okay. What about the other ones? Okay, what is a new line? I mean, you guys know about what a new line is. Okay, a new line moves the text to the following line. But depending on which terminal emulator you're using and what is the operating system, it may or may not go back to the beginning of the line. Because to go back to the beginning of the line relies on yet another control code. What is that one? It is a CR, it's a carriage return. What is a carriage return? We don't have horses on the keyboard. Yep, yep. On a typewriter, the carriage is the whole mechanism that is holding that piece of paper that you are typing on. That's the carriage. Okay. So carriage return is moving that entire mechanism back to the home position, but it doesn't do the line feed. Line feed is rotating that drum by one line. Carriage return moves it horizontally. So line feed and carriage return are two different mechanisms on an actual physical typewriter. So when you come to the digital world, then you have all kinds of confusion because in DOS, when you need to specify a new line, it'll be represented by a line feed and a carriage return, just like a typewriter. In Linux, it is just a line feed character. It will automatically do the carriage return for you. In the original Mac OS, it is just a carriage return. It will do the automatic line feed for you. So between the three main operating systems, you have three different standards of how to end a single line in a text file. You can kind of imagine the kind of confusion that can cause, right? You create a text file in one operating system, you try to load it into the editor like a plain text editor in another operating system. It's like, how come everything is on the same line? Or why is it looking kind of funny like a staircase? So that is ASCII code, okay? And I cannot even remember why I talked about when talking about ASCII code. Right. Okay. So the octal number, if you put a backslash in the C string and you go like, okay, backslash, okay, let me pick one that's kind of fun, bell, B-E-L-L, bell. So if you put in backslash 007 in a double quoted string and you try to print out or see out that thing, your terminal would actually make a beep. It still interprets the bell character to make a beep. So next time you want to really annoy your professor when your professor is grading your homework assignment, just put a lot of bell characters into your literal strings. So when your professor, when Herman is grading your homework assignment, it's like bing, 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 bing. And then Herman is going to talk to you and go like, why are you putting all these bell characters? And your answer is because text said that this will annoy you. All right. So I think this is a good sidetrack to talk about octal number because they were around, but we don't use them all that much anymore. All right, so getting back to this, okay, getting back to our example here. So now that we have this particular conversion table, which basically means group the digits, group the base two digits of the bits in groups of four. And then for every group of four, convert it to a single base 16 digit. That's how you do the base conversion. Okay. So that means, oh, okay. So that means I can now convert this entire thing into a hexadecimal representation. So I have one. Okay, so I'm going to rewrite this by but grouping things in a different way. So I take all these original spaces out and then we group by four. So 1100 is one group, 0000 is one group, 0011 is a group, 1010 is a group, 1010 is a group, and then the rest are all zeros. Okay, so now we can convert this into hexadecimal. This is a C, that's a 0, that's a 3, that's a A, that's a A. And because each hexadecimal digit is going to be responsible for 4 bits, so I need to make up 64 bits. How many more hexadecimal digits do I need? How many hexadecimal zeros do I need to make up for the rest of the digits? So I need 16 digits altogether, and I got 5 of those already. So that means what is left? 11. But you got it. I think you got the conversion done. You just did not know that I'm asking for how many more digits do I need. So the answer is 11. So okay, that's reasonably not too many to handle. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Extra one. We're done. So now we now look at this whole thing and go like, okay, tech, is this really legit? I mean, can we actually use this in C++ programming? The answer is yes. Okay, the whole 0x is a prefix to tell the C compiler what is following is a base 16 number. Okay, so now we have this number in base 16, and that's what text said should be representing 26.625 if we interpret this bit pattern using the IEEE double precision floating point number format. That's a lot for me to ask you to believe, and I'm not asking you to believe in it. So we're going to test it. Okay. So the question is, but how are we going to test this? This seems really awfully complicated. Well, the way we're going to test this will take no more than 5 minutes, depending on how quickly I want to kind of go through this. Okay, so this is what I'm going to do. I create a program that can help me with this. Okay, I'll just call it simple. So simple is a regular C function, and with the only exception that I have to include stdint.h, which stands for standard integer.h. So that would give me very specific type definitions like uint 64 underscore t. So this is the type name of a 64-bit unsigned integer. Even if I use this on an Arduino, it means a 64-bit unsigned integer. If I'm using a 32-bit compiler, it will still mean a 64-bit unsigned integer. In other words, this type name is independent of the architecture of the compiler that you're using or what you're cross-compiling to. It does not matter. It is always 64-bit wide. Okay, which to us is really important in this case. So I'm going to put a 0 into it, okay, which has nothing to do with what we are doing here. Save the program, gcc-d-o simple.c. Okay, the whole thing's compiled. GDB, which is a debugger, go into here, list the program. I'm going to put a breakpoint on line 7, run the program, okay? And you say, what can we expect here? That's pretty much what we can expect. Okay, you go like, but this has nothing to do with what we are doing here. Wait, we can do this. Okay, so I can use a command in GDB and say, well, let's put a specific value into the variable x. And that would be in my editor here. I'm not sure whether I can mix uppercase and lowercase. I think we can, but I suppose we'll find out soon enough. Like so. Okay, it took it. Okay. So you go like, okay, so what happens when we print x? That's not 26.625 or negative 26.625 because this number, okay, is the unsigned interpretation of this particular bit pattern here. It does not understand that I wanted to use the double precision floating point number way to interpret the bits. It really is just doing a VU x comma 64. If you don't remember what is VU something, you might need to kind of go back to a previous lecture. But it's the unsigned interpretation of those 64 bits. So sure enough, it's like, that's not what we want. So you go like, but I remember my CISP 360 professor taught me about, typecasting. Okay, so that will do the job? Nope, it's not. Because what it's doing is it is taking the unsigned interpretation of x, which is what we saw earlier, and then convert that into a double. In other words, the value being represented is still the really huge number here. So you go like, but how are we going to do this? Well, I'm going to give you a few questions then. Okay, what is this? What is the ampersand of a variable in C++? Hmm? Is the address of. Okay, so we are looking at the address of x, which is just some random location in memory, and it has a type of uint64 underscore t and an asterisk. Okay, which is exactly what we expect. It is an address of a 64-bit unsigned integer. It's like, okay, what of this? So now we go like, okay, let's do something like this. So what I'm casting is not the value. I'm casting the address. In other words, what used to be the address of a 64-bit unsigned integer is now the address of a double. I'm basically doing something illegal in the residential area and say, let's pretend that I have a commercial license of this particular partial code. Is that okay? So now you go like, okay, press the enter key, nothing happens, right? It is still at the same location, except instead of being a residential address, now it is a commercial address. I'm only one step away from what I really want to do. Tell me what is there. Because now, when I dereference this thing, it's going to go like, oh, okay, I see that you have the address of a double, and you're asking me what is at this address. I'm going to interpret what is there as a double. And then we get our negative 26.625 back. This is all the stuff that you have learned, or supposedly learned, from Cisp 360. Now, if you say, but Tech, we were never taught to do tricky stuff like this, fine, fair, completely fair. But you should still be able to understand what I did. Okay, step by step, what did I do, and what concepts are involved in what I just did. So coming up with a solution is very different from understanding a solution. Do I expect you guys to come up with these tricks? No. But do I think you should understand the approach and understand, oh, okay, this connects back to what I learned in Cisp 360? Yes. Are we good so far? Okay. So we are exactly running out of time. Okay. I do not time my lectures. It just turns out that way. Um, so that's the end of today's lecture. We do have a lab today on, I think this one is on two's complement, if I remember correctly. I cannot remember. It is going back to, we are not even done with subtraction and compare. Okay, this is two's complement. So that's your lab for today. It should be visible now. And this is the access code. It's just negative. So it's just negative, like so. So when you're done with this lab, you can go ahead and start your lunch break earlier. I don't think that this is going to take you a whole lot of time, but that's your lab. Are we good so far? Good. All right. So I'm going to stop the recorder and get it up.